Welcome back, everybody. So we left off last time talking about composition of functions, um, and we will get to this one in a second. Well, actually, now we can do it right now. That's fine. Um, well, I mean, we can even keep this here. That's still a valid point. So the difference quotient, the DQ. So this is not no longer f of x, but it doesn't really matter. Remember, the name of a function doesn't matter. It's just a name. So instead of f of x plus h is going to be g of x plus h minus g of x all divided by h. And so this is one where it's not going to require too much work to compute g of x plus h at the same time. However, I like to just do it off on the side anyways. So that's going to be 16 over x plus h plus 9, because the x is going to get replaced with an x plus h, an x plus h. So that means that this is going to be equal to 16 over g of x plus h, which is 16 over x plus h plus 9, minus g of, oh, and leave a little bit of space, and then write your minus sign. And then g of x, which is given, 16 over x plus 9, all divided by h. And if you'll remember, the key thing from this one, difference quotients, you're not done with the simplification until that h in the denominator has gone away. Once that h in the denominator, the big denominator has been canceled, once that h has been canceled, we're all set. So if this is something you've never seen before, don't panic. Say, well, what could I do? And as soon as I see fractions, I think I don't like dealing with multiple fractions. Maybe I can make this easier on myself by combining common denominators. So I'll multiply this one by x plus 9 over x plus 9, and the second one by x plus h plus 9 over x plus h plus 9. Then I'm happy to go through an extra step if need be, but this should therefore be 16x plus, what's 9 times 16? I don't have that off the top of my head. I guess 90 plus, what is it? 96? Interest. Uh, if it had been if it had been 6, then you'd be right. 144. Oh, because it's 12 times. Like you could break the 16 into a 4 times 4 and the 9 into a 3 times a 3. That's 12 times 12, which is 24. Oh, 144. So 16x plus 144 minus, in parentheses, 16x plus 16h plus 144, all divided by x plus h plus 9 times x plus 9, all divided by a bigger bar. In fact, I'm going to make this larger font, all over h. So by multiplying by what I did in red and in blue, I have guaranteed that these two fractions in the big numerator will have the exact same denominator of x plus h plus 9 times x plus 9. So I can just immediately combine the numerators, the small numerators together in that way. And I will go from there. So as a reminder, you can think of h as h over 1, right? So we can treat this as division by a fraction, so you can flip and multiply. So this is equal to 16x plus 144 minus 16x minus 16h minus 144, all divided by x plus h plus 9 times x plus 9 times 1 over h. just to make sure it's very clear where that 1 over h is coming from. That's from the denominator. So I was treating it like a fraction by writing it as h over 1. And then that's the same thing as flipping and multiplying. So I got that. And then the nice thing is that these 16x's cancel. Oh, that's supposed to be a 16h. The second one's supposed to be a 16h. I think I said 16h, but I wrote 16x. And the 144s cancel. And so this is equal to negative 16h over x plus h plus 9 times x plus 9 times that h, because when you multiply two fractions together, you multiply across. And then therefore the h's cancel. And we have our final answer, which is negative 16 over x plus h plus 9 times x plus 9. And that, now that the h is canceled, we are officially done. Sure, we'll use a pentagon. Why not? There's a lot of algebra there. And so you might think this is a very niche thing. This will never happen again. I frequently give one of these questions on my calc exams. One of the questions where, I mean, it's a little more technical than this because it involves limits and it involves like derivatives, but this is something they have to do. So it's once again further confirming that the algebra is the hardest part of the calculus. It's if you can do the algebra, it becomes a lot more relatable. So to recap one more time, the key thing is to find a common denominator so you can combine the two fractions in the big numerator. And once you do that, then you've got 16x plus 144 minus 16x plus 16h plus 144 in parentheses. You distribute it, and then you're going to flip and multiply by the fraction h. We're going to treat it like a fraction as h over 1. And so nicely for us, a lot of the stuff cancels except for that negative 16h, but it's going to cancel with the h that got into the denominator, leading us to our final answer, which is negative 16 over x plus h plus 9 times x plus 9. JT.
I had,
Yeah, sure.
if it would have been times like 2h, would it have canceled the h's and then made the negative 16 and negative 8 too? Or
Yes.
okay.
Yes, so just so that people will watch the recording know, JT is asking if there had been a 2h here, then this would be a 2 as well, and that would cancel that out. Is that right? That's what you're asking, yeah. And then so it would then be negative 8. But and then other question?
Cross section. So the x plus h in like the very beginning
Mhm.
we were doing. Remember, so you put the h, how come it goes only to the bottom where the x plus 9 was?
Because we're going to be replacing the x, any instance of x, with an x plus h.
Okay.
That's what we're doing. So like in short, so the reason.
So there's multiple x, you put x plus h both.
Exactly right. So wherever you see an x, you're going to replace it with an x plus h. Exactly right. So if there are multiple instances of x, then you'll replace all of them with that x plus h. But the big reason for that is that if you have g of a blue box, it doesn't matter what it is inside the blue box. The function, what it does is it takes that blue box and plugs it in. So this would be equal to 16 over blue box plus 9. And so what we're going to do is we're just going to plug in x plus h here. And that is a very, very important thing. This is a really hard thing, even for my calculus students. They still mess this up every once in a while. So it's a valid thing to think about. It's important to know. It feels weird because like we're so used to being able to plug in just x or like a different variable, but as soon as we like our function is in terms of x, but we're plugging in x plus h, it just feels a little bit strange at first. So thinking about it as like you're putting in whatever you want into it, and it just goes into where that variable is can kind of help.
Letters going on, and it's making me just like.
Ah, I see. I see. And how do we fix that? How do we work around that?
You did that formula. You'll give it to us for the test?
Oh, yes, absolutely.
Which ones, you said there's ones where you wouldn't?
Just function composition. So function composition, which was this next thing. Um, but I'm gonna think on what Ronnie was saying about like the dyslexia starting to kick in because I get you. There have been times like there's a an area of mathematics called differential equations, and there's a thing where it's the method of undetermined coefficients, where basically you get a function and you have to write it. You have to find the coefficients, and it becomes like a t cubed plus b t squared plus c t plus d plus e cosine t plus f sine of t. I remember doing one of these things, and it's a lot of letters to keep in mind, and it starts to become very, very daunting. But the good news is with a lot of these things, it always has a like mathematicians, we like while we are very, very technical, and we and sadly from our get-go, from its formulation, it was very, very elitist and things like that. And so there were many ways that we tried to make it exclusionary as mathematicians. At least we were trying to stay consistent with things and trying to make things work out. So like even if it is looking intimidating, it will work out, I promise you. It's kind of the old adage of just keep chipping away at it, and eventually it will break down. Uh, any other questions? I think JT, you had a question. Okay. Of how do we know this g of x plus h? Was that
Yeah, I was just confused.
for sure? Fair enough. Any other questions? All right. So to recap from last time, the main thing, composition. What it is it looks like a little open circle in between the two functions. And so it looks like fog, but what you're saying is f composed with g of x, and it's defined as plugging in g into the function f. Plugging g into f. And then what we learned is that function composition is not commutative. So we had an extra example to kind of further prove that, right? Oh, did we finish both of them? Yes. Wait, did we? No.
No, I think we got to the first one. Ran out of time.
Oh no, we did. We did. I just didn't box this one for whatever reason, I guess. So just showing you that the two versions, it's not commutative. It's not necessarily going to be the same thing. I keep trying to get to the pointer, but it's not giving me the pointer. So it is not enough to just find one version. Like if it asks you to find both, it's not sufficient to just find one. You have to find both. And then simplification, once again, is kind of for chumps. We don't need to simplify unless we're absolutely forced to. Yes. Yes,
Oh, I
JT.
don't know, sorry, you looked down, I don't know if that was a college. So is there like a trick or anything where it's, they're opposite, like F of G and then G of F, like where you can like leave the square, some weird thing to get to the answer, or do you just have to redo it?
It just has to be redone. It is a situation, sadly, like there are situations where it will work out one way or the other, but it's very few and far between.
Got it.
Okay, so last thing about this is how do you find domains of composite functions? Because they play a role, and it becomes a little bit strange. And I've deliberately catered this example to go through this strange situation and why we have to do it in this kind of order. And it really, if we really understand what the definition does, it will make sense why we do it in this order. So first things first, you're going to find where the inside function is undefined. So we're doing f composed of g of x. So g is the inside function. So g of x is equal to x, the square root of x plus 3 And so we're trying to find where its domain, essentially, where it's undefined. And in order for this thing to be well defined, we need the inside to be greater than or equal to 0. So we need x plus 3 to be greater than or equal to 0, which means that x needs to be greater than or equal to -3. And so the reason why we have to do this is, I'll let you write down to it. The reason we have to do this step is because of how it's defined. Once again, and so you don't need to write this down, but this is just for us to look at it. F composed of g of x, by its definition, is f of the quantity g of x. So if I can't plug in that x value into g of x, it won't work. It won't, like, I'll be trying to plug in undefined. Case in point, I think I put that down there. So I'm getting ahead of myself. But we'll further expand upon this at the end. But in order for me to actually even compute anything for x, I need to make sure that it makes sense in G. Otherwise, I can't plug it in because of how composition is defined. It needs to be able to be plugged into the inside function, meaning that we need to look at the inside function to see where it can be defined. We need to make sure that the inside function is well defined. Step 2 will be to find the composition function and simplify where necessary. And this is a situation where it does fall into our task of we're going to be using this, so we should simplify. So f composed of g of x is equal to f of the quantity g of x. And I'm writing that just so that we get practice remembering what it is. Though if you want to go straight to just writing down the answer and stuff like that, you can skip some step if you want. But that's going to be f of the square root of x plus 3. And so that means that in f, I'm going to replace every instance of x. There's only one instance of x, it's the x squared, but I'm going to replace every instance of x with a square root of x plus 3. So this becomes 1 over x squared, which is now going to be replaced with an x squared of x plus 3 quantity squared minus 8. And that, in that situation, the square root and the square cancel. And we end up with 1 over x plus 3 minus 8, which is 1 over x minus 5. Take a second to digest. Yes.
I had a question about that one. I don't know if it would ever actually come up, but if like when you're solving for G of x and trying to figure out if that would have been just like a single number, like if it was a fraction, it was a single number on the bottom, and so like it couldn't work, would that how would that just mean the problem's like an undefined problem?
So if it's a so are you talking are you talking about like a function like this? Opposite. X over 2, like something like that?
Yeah.
Well, then that thing has no problems, right? There's no problems with x over 2. So its domain is everything, and so you can plug in whatever you want into it.
Oh.
It's when you have we want to avoid dividing by 0 and taking the square roots or even roots of negative numbers. That's the key thing for now. Right? And then find the values that make the result from step 2 undefined. So we just found that f composed of g of x was equal to, when simplified, is equal to 1 over x minus 5. And so we get that x can't equal 5, right? Which starts off by saying that x minus 5 can't equal 0, but that's a very quick calculation to say that x can't equal 5. And so to find the domain, after that information, we just need to combine the informations from steps 1 and 3 to find the domain of our composition function. So from step 1, x needs to be greater than or equal to -3. And from step 3, x can't equal 5. So you might be able to see this already, but if you don't, we can use a number line. Here's -3, here's 5. The pink says everything to the right of 3, but the orange says that 5 has to be plucked out. So we just get 2 pieces of intervals. The domain is equal to bracket -3 to 5 parenthesis union parenthesis 5 to infinity. Taking that information, we know that x has to be greater than or equal to -3. So we're all the way to the right of 3, and to the right of -3 and including it. But from the orange, from the composition function itself, it won't be defined at 5. So we also have to pluck that out. Now, if it was -5, that would be outside of the scope, so it would be vacuously satisfied. But here we lucked out. So I hinted at it before, but once again, why step 1? It looks like if you're looking at the simplified version of f composed of g of x, it looks like it's defined for everything except for x equals 5. And the answer is, as we said, it's how composition works. Let's try to plug in x equals negative, let's make it a nice number. -4. Yeah, just x equals -4. So f composed of g of -4. If we weren't to do step 1, we would assume that everything was fair game, from -infinity up to 5, union from 5 to positive infinity. But because of how function composition works, this is saying this is equal to f of the quantity g of -4. So we have to be able to plug it into g in order for it to work. But as we can see, g of -4 is equal to the square root of -4 plus is it +3? Yeah, +3. Which equals the square root of -1, which is not a real number. So it's not a real, it's not included. Can't plug in g of -4 into f. Yes, Jason.
Use all the questions, saying that like asking why we did it because it has to be greater than -3.
So the question is like, why did we need to do step 1? Why do we have to do that? Why couldn't I just look at because in the other situations, right? In the other algebra functions, like the product function, the sum function, the difference function, the quotient function, all those ones, all we needed to do was just look at the result to find it. Why do we have to look at the inside function in this case? And partly it is because, I mean, technically speaking, I guess, backpedaling just a small bit, we are looking at each function in the previous situations. We are looking at them. It's just we're combining them first and then looking at them holistically before simplifying. But the same thing is kind of true here. So the reason, like, why step one? The question is asking, why do we need to do that? Why do we need to bother that instead of just looking at the whole function holistically? And I suppose there, like, you could do it in a certain way that's different, but this is the method that I've kind of concocted, and it's mainly meant to show that composition, it has a sequence to it. It's you're plugging in the x value into the function g, and then you're plugging in that value into f. It's kind of this step-by-step process. It's this first you plug it into the first function, then the next function. And in fact, you can do this actually, there is later on, we can see you can get functions like f composed with g composed with h. Or you can even do this even further. You can do f composed with g composed with h composed with k of x, right? But the key thing is understanding how it works. So this function right here, what it does is it first plugs it into, so it becomes this, is weird, but f composed with g of the quantity h composed with k of x, like that. So it gets plugged into the inside function. It's a sequence of things. So you have to be, it has to be defined in the inside function in order for it to even be plugged into the next function. It's kind of this like snowball effect, essentially. Don't worry about this. This would never happen. This is a very, very weird situation, but yes.
So basically you're just starting from, so it'd be like k of x, and you plug that into h of in.
Exactly right. Exactly right. So to continue on this project process, we need to first be able to plug it into k, and whatever that value is, we need to be able to plug that value into h. And as long as that value is defined, then we can plug it into f composed with g, which means we really need to just be able to plug this whole value into g so that it can be plugged into f. So it's this real sequential relationship. It's all about making sure that it can be plugged into the first function available. And if it can't, then there's a problem. So that's the reason for step one, is that we need to worry about being able to plug it into the inside function from the get-go based on the definition.
Okay.
I'm glad. I love the questions.
So this, probably I should have already known. So this is just saying, like, even when it's that long sentence, it's just saying like the domain means any of the numbers that fit in between what's not like part of the domain, like what's x out of the domain, that can fit into the first like letter.
Yes, the first function.
Okay, okay. Now I think. So that's why the domain's the answer.
Yes. Yeah, because I mean, the question itself is saying find the domain. We did a lot of stuff here to finally get to that statement, but so let's do another example. And this one will help us figure things out as well. So given that f of x is equal to 1 over x and g of x is equal to 5 over x minus 3, find the composition g composed with f and its domain. So we're going to be working with g composed with f of x. And as an aside, so step one, if we want to break it down, is to look at the inside function. The inside is f of x, which is 1 over x. And that gives us the statement that x cannot equal 0, right? If we're going to be able to plug in x values, if we try to even plug in 0, we're going to be doing g of f of 0, but f of 0 does not exist. That's step one. And then step two is to actually compute it. So that's g of the quantity f of x, which is g of 1 over x, which is going to be 5 over. We're going to replace every instance of x in g, which in this case is just one situation. There's only one x that's present in the equation that is g, just the x in the x minus 3 portion. Let me say that slower because my words started to slur together. There is only one instance of x in g, And it's in the denominator, that x minus 3. There's just one x. So we're going to replace that singular x with a 1 over x because we're plugging this into the function. We're plugging that into g. So it's 1 over x minus 3. And so we can simplify it. We could also just look at this holistically. That is the other way to do this, is to look at it holistically first. But with my method, this is the proper way to do things. We want to simplify it, so we're going to find a common denominator. So we'll multiply this by x over x. And so this will equal 5 over 1 minus 3x over x. And so what I will say is you could technically skip step 1 if you wanted to work from here onwards and like look at this, like and say, okay, well, first and foremost, x can't equal 0. Otherwise, the denominator would have a dividing by 0 situation, and that's a problem. But either way, this is now 5x over 1 minus 3x. And we know, therefore, that, let's use purple. 1 minus 3x can't equal 0. So x can't equal 1/3. What we'll do is we'll subtract 1 from both sides. You get negative 3x equals negative 1. Divide by negative 3. You get positive 1/3 because the negative divided by a negative is a positive. So from here, we just need to look at a number line. We found the two things. So step 3 is combining all that information. Well, I guess that step 2 and step 3 were right here. And then step 4 is to combine all that information. So on a number line, though, if you've got it already on lockdown, cool. 0 and 1/3. From the red, 0 is excluded. From the purple, 1/3 is excluded. And everything else is fair game. So the domain is parenthesis negative infinity to 0, union 0 to 1/3, union 1/3 to positive infinity. I can box this answer in. It also said to find the G composed of F, so I guess I should also box this in as well. Yes, JT.
It's asking us to find the domain, not find what the function is. Couldn't we just take on step 2, we could just do 1 over x minus 3 equals 0, right? Because that would just find the domain.
That's true, yes.
Okay.
Yeah. You could also set, like, you could do that as well.
Okay. That's what I did. I just
Set 1 over x minus 3 not equal to 0 and solve for x.
Yeah.
That would honestly probably be correct. And honestly, I believe Alex will accept you leaving it as 5 over 1 over x minus 3. It might do that passive aggressive comment saying it could be simplified, but you can just say shove it because it's.
Does that count as an answer if it was 5 over 1 over x minus 3?
Yeah, that's valid to me. I'll accept that. And if Alex doesn't, let me know. I'll give you full credit back. Okay. So, any other questions on this one? Okay, if there are, even if we're lost. Yes, Jiggy.
You just got the 5x over 1 minus 3x by multiplying.
Yeah, by flipping and multiplying. Because we're divided by a fraction, you flip and multiply. Okay. Now we come to one of my favorite problems. I love this problem very, very much because it's a super cool abstract problem. Because you're looking at it and you're saying, Okay, you're given the graph of f and g, one of them in red, one of them in blue. And asked you to find f plus g of 0 and all these other things. And at first glance, it's like, well, I don't have the functions. I can't plug it in. But we got to remember our understanding of functions, what it means to be a point on a graph. So all we really need to do, and this is worth like 1 point if this shows up or something like that, is to say, okay, well, what does f plus g of 0 mean? It's exactly what we think it means. What we think it means. It is, by definition, f of 0 plus g of 0. And so I'm going to underline this one in, let's do green. F of 0 is 4 and g of 0 is 2. So it equals 6. F of 0 plus g of 0, you just need to find the corresponding y values. That's what f of 0 is. It's the function value, the y value that gets associated on the graph to x equals 0. So g divided by f, the quotient function, g over f of 5. Once again, these, like the algebra functions, they are completely exactly what you think they'd be. There is no ambiguity here. It is exactly going to be defined as g of 5 divided by f of 5. And so let's highlight this one in maybe purple and find at 5. G of 5 is 1, f of 5 is 5. So this is 1 over 5. And that's as far as we can go. That can't get simplified any further. We'll do C together, and then I'll have you guys do D. I just like this problem because we can do things without even having to have any knowledge about what the function is. If we're just given the graph, we can still find information out. So G composed with F of -6. By definition, that is equal to G of F of -6. So I'm going to underline this one in orange. And so F of -6, F of -6 is equal to 2. And so this is no longer G of F of -6. This is G of 2. And what's G of 2? Well, we're looking for G when X is equal to 2. So maybe we'll do this one in pink. But I think, or no, let's do blue. G of 2 is -2. And that's our answer. So I want you guys to do G composed with G. G composed with itself of 0. If there's any questions, though, on the first 3, please let me know. All right. So go ahead and work through that. I'm slowly going to fill in details. be the same number. Could have done it maybe different. Like what if I do, oh, that's right. If I do G5, that doesn't work out. What if I do G of 2, -2? Nope, not. Well, we could do another one if you guys want. No. So like there is a like this would be a very, very challenging problem. But if I asked you what G of G like just as a fun little tidbit, if you want to do this weekend, it's a great problem. Great problem to do with your dad. You know, they're still around. They might be willing to help you out and make sure you get some plenty of tears out on that one, like my dad did for me. But no, my dad was delightful. But G composed G of 5. That'll be G of 5, right? And G of 5 is equal to 1. So this is G of 1. Oh, no, it's actually going to be that's going to be fine. That's going to be 0. Never mind. There are some situations. Let's see here. Is there one that's there is a situation that would be fun, where you'd have to create the equation of the line to figure out what the value would be, because it's not a nice line, but I actually just found, I'm going to change that one to G composed of G of 5. That'd be way easier. That'd be, so that's 1.8.8 D, 1.8.8 D. Okay. Thank you. There we are. Okay. One last thing about composition. And this is actually very, like, honestly, out of all the things in this situation, this is probably the most useful because composition is how the chain rule works in calculus. So there's a rule in calculus for differentiation called the chain rule, and it all stems on identifying a function as a composition of an inside function and an outside function. So given h of x is equal to the square root of 7 over x minus 22, find two non-identity functions, f and g, such that h is the composition of those two functions. So what they mean by non-identity is non-x functions. Because if you use x, then everything is very, very quick. Because if you just use x, then you can make the original the other part, the original function, and it becomes immediate. So we're trying to find two things that work. There's a reason why I've called them the inside and outside functions. Is the key identify the inside, quote unquote, and the outside of the original function. The inside and outside of the original function. And that is as straightforward as you think it would be. One of the cool things about these problems, by the way, is there's actually a lot of different options. There are infinitely many, well, not infinitely many, I suppose, no, there are infinitely many ways to compose two functions to create that, which is pretty nifty. But I'll show you, but the most intuitive way is to look at it purely as inside and outside. So what is the quote unquote inside? The inside of H. Inside, I'll put inside of H. It's the thing inside the square root. So it's 7 over x minus 22. So that'll equal g of x. That'll equal our inside function. remember, G, like in our terminology, since we're doing F composed of G, G is our inside function. And then our outside of H is the square root symbol. So the outside function is going to be square root of X. The outside is that square root, so we're going to make it a square root function. If this was instead, by the way, if this had instead been 7 over x minus 22 to the 14th power, this would be x to the 14th. That's kind of the outside thing. The outside thing was the 14th power, so we'll make it x to the 14th. If it was, well, those are the two situations we're encountering right now. And we can check our work. And this is good practice because it practices our knowledge of how to do compositions of functions. F composed of g of x is by definition f of g of x. And g of x is 7 over x minus 22. So this is f of 7 over x minus 22. And so all I need to do is plug in 7 over x minus 22 wherever I see an x inside of the function f. And there's only one instance of x. So I'm just going to replace that x with 7 over x minus 22, which is h of x. So we did it right. An alternative, by the way. So, but there are many more. Oh, yeah, JT.
I just don't understand like where do we, that cannot equal X, what does that mean in the original question?
Excellent question. So I'm going to show you, you don't need to write this down. The reason why they don't allow you to do X is because then the problem becomes trivial. So if I make f of x equal to x, then g of x just needs to equal the square root of 7 over x minus 22. Because then when I plug in g into f, it just replaces it and it's all done deal. Same thing for the vice versa situation, because then all I need to do is just replace the x in x minus 22 with an x, and it goes right away. That's what that terminology is just saying. It's just find two non-trivial functions. They say non-identity, and that's because when it and we'll see that actually. I actually kind of like teaching 1.8 now instead of the way I usually teach in regular 126, because I usually teach it in Unit 1 and 126 because they come in with a background knowledge of rational functions and rational expressions, and they know how to work with these types of things. We weren't given that opportunity, but this gives us a very good introduction on why it's called the identity function. And we'll talk about that in just a moment. But there are infinitely many options. You can check these on your own time. Another option would be f of x equals the square root of 7 over x, and g of x equals x minus 22. That's another such option. You could think of it as the truly inside of the inside of that function. The inside, like the truest inside, is that like x over 20, x minus 22. And so all I need to do is just replace the x with the x minus 22. I'm all good. That's one such option. You could also do, or you could do fx equals the square root of 7 over x minus 1, and g of x equaling x minus 21. Because then the x will get replaced with an x minus 21, and then you got x minus 21 minus 1, which makes it x minus 22, and we're all good. But I think you can see how you can just keep doing this. You can make it x minus 2 and x minus 20, x minus 3 and x minus 19, and so on and so forth. You can do, and so on. But the most efficient way and the best way to do it is to identify the true outside and the true inside. Not try and find clever other options. Sure, it's fun. I mean, no, it's not fun. Let's be real. It's not fun to create those examples. It's silly. I'll say that it's silly, but it will be far more useful and beneficial for your for calculus if you plan on taking it to just do it in the most immediate option available. So I've got another additional example here. I'd like you to try and do it on your own this weekend, maybe tonight, just to verify. But I've got a bunch of different, like as I say there are many answers, but the first one is the best choice. Okay. Any questions? All right. So that completes 1.8. And I think this is a perfect time to take a break. Let's come back at 10:02-ish, and we'll start inverse functions, which I didn't upload. Awkward. All right. So 10:02, 10:00 or 10:03. Say what? 3.1. We're going to be going to 3.1. People who are watching the recording, go stretch, do some guided meditation. I wanted to mention this because it made me so angry. It made me so angry. Is the show Psych. Love Psych. Love great show. There's a show where they go to an engineering magnet school for high school, and the kids have this on their lapel. They have this. And so that is an integral symbol. This long S is an integral symbol. E is the exponential function, which we're going to talk about very soon, and then X, Y variables. And so Sean asks Gus, what is it? He's like, well, that's the integral for the area under the curve X, Y. And there are so many things wrong with that statement. There are so many things wrong. So yes, it is an integral, but because it is a two-variable integral, it is now not an area. It is it's not an area. It's a volume because it's a multivariable function. It's going to be a surface. And then also it doesn't even have, it's supposed to have a dx dy here. And I get the reason why is it's supposed to say sexy, right? With the elongated integral as an x. But the fact is he's saying it's an area of a curve. It's not a curve, it's a surface. And it's not an area, it's a volume. And it's also just not written correctly. So I wrote the writers. I didn't actually, but I probably should have. But anyways, getting sidetracked. Inverse functions. So the reason why we wanted to wait until now to talk about composition is partly for this. And sadly, we need to take a small detour, and we're going to try and rush through this because it's not super important in the grand scheme of things, but it's mainly meant as a precursor. So a function is called one-to-one, and I hate writing this. They say one-to-one. However, I think whoever decided to do that terminology, they had a good idea when they wanted to change the name. But the problem is that in later mathematics, one-to-one can mean something completely different, like a better version of what one-to-one actually is. So I don't like that terminology. The actual terminology that most mathematicians will say is they'll say injective, which just sounds way cooler. So you say that's an injective function, and now people are really, really impressed by you and intimidated. So I think that's the reason why it should be injective. But either way, we're going to say one-to-one, and it's going to kill me a little bit on the inside, but either way. A function is one-to-one if no two x values share the same y value. That is, each x gets sent exactly to one unique y value. There are no so we can't have things like f of 5 equaling 2 and f of -2 equaling 2. Let's do -1. It's very, very similar to the line test, in fact. So the vertical line test was talking about whether or not something was a function. And in that situation, it was that no x value gets sent to two y values. In this situation, it's kind of the opposite. It's that no two x values go to the same y value. Instead of one x going to two things, it's two x is going to one thing. So it's the reverse option. So we can't get things like f of 5 equaling 2 and f of negative 1 equaling 2. That is no longer an inverse, like that is no longer a one-to-one function. Mathematically, which I don't want, like I'm going to show you what the definition is, but this is mainly used for upper division mathematics. Like if you decide to take Math 251, which is Introduction to Mathematical Reasoning, you might talk about it there. And if not there, then the next time you'll actually start talking about it is in a 400 level math class. Or an intro to proof class. So mathematically, what it's saying is that if f of x sub 1 equals f of x sub 2, or let's write the better version of it. If x sub 1 does not equal x sub 2, then f of x sub 1 does not equal f of x sub 2. I could give you the formal definition, which is what we call in mathematics and in logic the contrapositive. And if you want to know more about, like, I highly encourage you all to take a philosophy of logic class. It's a very fun class. It's all about realizing how structured arguments are supposed to work. And you also start learning about how, like, you know, like we can make constructive arguments, but at the end of the day, arguing, you have to assume the best interest in the other person. You don't try not to assume that they're saying bad things unless they elaborate and say the bad things, because words are very, very bad communication tools. They're the best we have, but they're bad. Either way. So that's the mathematical definition. You're not going to be tested on that aspect. To show you an example, R, the first one, that set of collection of that collection of points is a one-to-one function. You'll notice that it satisfies the vertical line test, right? No vertical line crosses through at more than 1 point. But you'll see that the x value, let's see here, where is it? Sorry, no, this one is a one-to-one function. And you see that no x value gets sent to the, like all x values get unique y values. So there's no repeats of y values. However, with the second one, notice that the x values this is one of the problems. X equals -2 and x equals 0 both get sent to y equals 4. Additionally, we actually have two problems. We also have this one here. -3, 1, and 1, 1. And x equals -3 and x equals 1 get sent to y equals 1. So, I mean, as the next line kind of gives away what's happening, unfortunately. I should probably just get rid of that name. I should the blank test. So because what is it that determines whether or not a function is going to be one-to-one? A horizontal line. Oh man, I gave it away. If you draw a horizontal line through this graph, it crosses twice here. It goes through the same, like remember, a horizontal line is y equals that number. So in this case, y equals 4. And so every point on that line has the exact same y value. So that's the problem. We have a situation. This is why it's not one-to-one, because it crosses at more than 1 point. So a function is one-to-one if and only if no horizontal line crosses the curve, or let's say intersects the curve. More than once. No horizontal line intersects the curve more than once. Then it's a one-to-one function. So that's the horizontal line test. Very similar to the vertical line test, just flipped. And it's not about choosing whether or not something's a function. It's about showing whether or not a function is one-to-one. So this first example, all we need to do is find one horizontal line, and then it breaks. And so for this one, we have, this is not one-to-one. Whereas this next one, if I draw any horizontal line, it always intersects it only once. So this is one-to-one. Yes.
Curiosity, is there like 2 to 1, or I guess 1 to 2 and different ratio functions?
Interesting. Actually, there might be in mathematics. Maybe that's something that that people are studying. That it's not very useful locally, like for most math courses, but it might be something that people are studying. That is there might be something about like a 2-to-1 function, like making sure that like only x values get sent to like 2x, like you can only have one situation where 2x values or something like that. There might be, and that would be a cool thing that would definitely be a situation. I'd see that happen in a grad school dissertation or something. Someone was deciding, well, what happens if now, and then seeing if there's any fun functions that pop out with that concept. So we're going to determine whether or not these functions are one-to-one. And so the first one is given a graph. What do you think? 1-to-1? Yep. Yep. 1-to-1. Because you can draw any horizontal line, it doesn't intersect it. But part B, oh no, we're given the equation. But that's okay. We know how to graph that. It's a parabola. And the vertex with vertex 3 comma, I'm gonna plug in 3, get 9 minus 18, -9 plus 4, -4. So right there, and it's gonna look like this, roughly speaking. Exactly how accurate that is does not matter, because we're not really looking for a perfect picture. We're just looking to see if it's 1-to-1 or not. And this one, not 1-to-1. In fact, any parabola is not 1-to-1. You're gonna ask that? Yeah. All parabolas are not 1-to-1. Part C, oh yeah, JT. They are still parabolas. They're just, and that is something you like, depending on your teacher, some 127 instructors skip it, but there are sideways opening parabolas. They're no longer functions, but they are still parabolas. Part C, not 1-to-1. And then part D is deliberately an example to show once again that the open circles matter, right? Open circles mean that the function doesn't exist there. It's a placeholder. It's meant to show you where the function starts back up again, but it's not actually there. So the only, like, we can see everywhere else besides the line y equals 2, we're going to have no issues. And so instead, but the only one that we need to worry about is the space right there. It doesn't, open circle implies doesn't exist there. So we're good. So this is 1-to-1. Any questions on it? It was the same thing with vertical lines, right? If there's an open circle and there's a solid dot above it, it is it is a function because it just goes straight through the hole of that open circle. Okay. So the question that I hope you're wondering is why? Why are we studying this? Why is this another thing that Phil's throwing in my face, saying, oh, it's got another thing we got to learn? It is mainly meant as a setup to inverse functions. So in order for a function to have an inverse, it needs to be a one-to-one function. And I'll explain why in just a moment, but there is a later concept, like, so when I say inverse, what I actually mean is a global inverse function and an inverse function that's defined everywhere. There is such a thing as a local inverse function. Almost every function can have a local inverse, but only one-to-one functions have global inverse functions. So if you're a one-to-one function, then it is automatically true. Like you don't need to check it or verify or anything like that. If your function is one-to-one, then there exists a function g such that f composed of g is equal to f composed of g of x is equal to x, and g composed of f of x is equal to x. So that when you compose it with itself, when you compose the two functions together, sorry, that went off the page. Regardless of how you compose it, you get back x. This function is called the inverse function, the inverse of f. And it is denoted f with a -1 up top. This is the one place where mathematics really becomes frustrating. Like, well, not one place. There's many places where mathematics becomes frustrating. But this is one notation. I wish there was a different thing that we had thought of. I understand why we do it, why we use that notation, but that gets it confused with an exponent. It's not an exponent because remember, a negative exponent, if I write x to the -1, you don't need to write this down, but this is 1 over x. But f the -1 of x is not equal to 1 over f of x. That's not true. So that's a frustrating thing of the notation. I wish they used f's upper script I or something like that for inverse. It would make things a lot more clear. But you'll see this again if you plan on taking trigonometry when they want to write the inverse of a cosine or a sine. So when we want to say cosine of a value squared, we write cosine squared of x like that. We don't put it over here because it looks confusing. And so they put it there, and so that makes it look like an exponent. But when they talk about inverse cosine, they write it like this, and it's not an exponent. So it's a very, very frustrating situation. I think why don't we just change it to an I? That would make way more sense. I for inverse. But then again, that's me speaking from a privileged point of view of being an American, and we call it an inverse, which starts with I, but I imagine in Japan, inverse doesn't start with I. I imagine inverse starts with a different character. So I guess that's probably why not. But anyways, it's denoted f raised to the -1. That is not an exponent. It just means that's the inverse. So writing it in the proper format, that is to say that when you take f composed of f inverse of x, you get x. And when you do f inverse composed of f of x, you get x. So that's an inverse function. And this tells us why the identity, why we call x the identity function, by the way. And so you don't need to draw this, but this is just for your understanding of why it works. So some people, when they're trying to explain functions, they like to think of it as the domain and the range, right? Domain and the range. The domain is all the x values that get plugged into the function. The range is all the y values. So a function goes from the domain to the range. It takes in an x value and spits out a y value. but the inverse function goes the opposite direction. It goes like that. So it takes a y value and maps it to the corresponding x value. So, for example, if I have 1 here and maybe 3 here, and I have 4 and 5, if I go like this, like if the function, I should make this green, blue, and I'll make this one red, f inverse. So the function will take 1 and map it to 4, and then maybe it takes 3 and maps it to 5. The inverse function undoes that. So the inverse function would take 4 and send it back to 1, and it would take 5 and send it back to 3. There's a reason why it's called the inverse of f, is because it takes what f does and undoes it. And so this is the reason why we can't have, we need to be a one-to-one function. This is an example of not a one-to-one function. The two x values, the x value 1 and the x value 3, both get sent to 4. But now if you're talking about going backwards, now your one value is being sent to two different things, making it not a function. Remember, in order to be a function, each thing needs to go to one specific thing. It can't go to multiple spaces. So in order to have an inverse, you can't be not one-to-one. In order to have an inverse, you have to be one-to-one. Otherwise, you end up with situations where one of your values will get sent to two different things at once, which is problematic. This is something, though, I don't really talk about this very often in 126, because this is something we really start to focus on in 251 and above. This is something mathematicians start to focus on. So, but in essence, you know two functions are inverses if they get composed and they give you back the identity. So that's why the reason why it's called the identity. Remember, 1 is the multiplicative identity, right? Because if I take 1/2 and I multiply it by 2, I get back 1. It's the multiplicative identity because whenever you compose, whenever you multiply the inverses together, you get back 1. More specifically, it's that whenever you multiply it by anything, you get back 1, or you get back to what you got. But anyways, that's why x is the identity function, is because it's what you get when you compose an inverse with itself. So to verify that these two functions are inverses, we need to show f composed of g of x is equal to x, and g composed of f of x is equal to x. Because remember, if these things are inverses, they are going to be, but if they are inverses, then they're the same thing. But if they're not, then f composed of g and g composed of f aren't necessarily the same thing, because it's not commutative, right? Composition is not commutative. Let's go ahead and verify those things. F composed of g of x is by definition f of the quantity g of x. And g of x is the cube root of x minus 1 over 2. So this is f of the quantity cubed root of x minus 1 over 2. And so what that means is that wherever we see an x in the function f, we're going to replace that with the cube root of x minus 1 over 2. F only has one instance of x in it. It's that 2x cubed, but still. So plugging that in, we get 2 times the quantity, the cubed root of x minus 1 over 2 to the third power, plus that 1. That's the function f with the cube root thing plugged into it. And isn't that nice? The cube root and the cube cancel. And so we've got 2 times x minus 1 over 2 plus 1. And isn't that nice? The 2's cancel. And so we have x minus 1 plus 1. And isn't that nice? The 1's cancel. And we finally get our final answer, which is x. So that one works. But that's not it. Oh, yeah, go ahead, JT.
Oh, the cubes cancel out, that cancels out the whole square root in general.
Yeah, it cancels out the radical. It gets rid of the, like, because the third root and the third power are inverses of each other, they cancel each other out. And they go, and they both go away. And so we did that one, but it's not enough. There is a weird situation, by the way, in mathematics that you may study if you decide to be a math major. I don't know why you would, but if you do, there are things called left inverses and right inverses. They're functions that they give you x on one version, but they don't give you x in the other version. So those are a strange situation, but we're not going to study those. Those aren't important. And then if we do g composed with f of x, that is by definition g of the quantity f of x. And f of x is 2x cubed plus 1. So this is really g of the quantity 2x cubed plus 1. Meaning that we're going to take every instance of x in g, in the function g, and replace it with a 2x cubed plus 1. There's only one instance of x in it, but either way. So this will become the cubed root of the quantity 2x cubed plus 1 minus 1 over 2. And isn't that nice? The ones cancel. And we get the cubed root of 2x cubed over 2. And isn't that nice? The 2's cancel. And then we've got the cubed root of x cubed. Oh, that's nice too. Those cancel. And we just get back x. So they are inverses. So yes. If we don't get back x when we compose one or the other, it's not enough to check one, you need to check both because function composition is not commutative. F composed with g isn't necessarily equal to g composed with f. But we did find that these things were inverses of each other. And that's great. That's fine and dandy, Phil. But how do I find them? How do I find an inverse function? And the thing you might be wondering, by the way, is yeah, one-to-one functions were just used to find out that inverses exist. What's the point of inverse functions? There's a lot of uses for them. In calculus, sometimes you don't know what the function is, but you can find its inverse. Like maybe you're given the inverse of a function, and you want to know the rate of change of something, and you want to know the rate of change of the original function, but you only have the inverse, and there's no way to find the original function. You can use a thing called the inverse function theorem from calculus to find out that value. So there are situations in mathematics where functions do have an inverse, but it's impossible to calculate. That's never going to happen to us. All of the functions we're going to be dealing with, they will have nice, neat inverses, but there are situations where it is impossible to calculate. And the inverse function theorem allows us to figure that out. It's a very, very nasty theorem. Took like 10 pages to prove it, but either way. So how do we find them? In order to talk about that, I want to talk about an observation. Why did that get all wonky there? This should be lowered, but either way. So the original function, f of x equals 2x cubed plus 1, and the inverse is the cube root of x minus 1 over 2. And so when you talk about a function, you can talk about it most of the time, or at least some of the time, about what it does to a number. And so the original function, f, what it does is it takes a number, and then it cubes it, then it multiplies it by 2, and then it adds 1. Whereas the inverse function, what it does is it takes a number, subtracts 1, then divides that result by 2, then takes the cubed root. So the point, the key, the inverse function undoes everything to x. So it basically goes backwards. It does the exact, it goes in the backwards direction with the opposite operation, right? Cubing at the first step for f, cubed rooting for the third step of f inverse. multiplying by 2 for the second step, dividing by 2 for the second step for F inverse. Adding 1 in the last step of F, the first step of F inverse is to subtract 1. So it undoes it. That's the intuition on how to find an inverse. So how do we find inverse functions? We do this procedure, and I will concede that I teach this differently than there's one minor difference that I do with regards to the step-by-step process. The book and most undergrad, most pre-calculus textbooks will swap step 2 and step 1. The step 2 is going to be interchanging x's and y's. And so they will change those 2 steps, but I disagree with that because that fundamentally misses the point of what an inverse does. So I do it this way. If you like the way that the book does it more, you can do it that way. It's not wrong to do so. But I mean, I will get into like I can go into a tirade on it in just a moment. But find the inverse of f of x equals 2x minus 5. So first and foremost, to make it easier to write and easier to read, we're going to replace f of x with y as needed. So maybe it's just saying find the inverse of y equals 2x minus 5, in which case that step is not necessary. But in this case, it is. So we're going to rewrite it as y equals 2x minus 5. Then what you're going to do is you're going to solve for x. You want to get to the point where you have x equals stuff with y's. So it should just be a singular x on one side and y's on the other. So in this situation, y equals 2x minus 5. What we're going to do is we're going to solve for x. So what we should do first is add 5. And I'm writing this down because this is our first time seeing it, but in the general, I don't need you to write this algebra. You can do it in your head. So we get y plus 5 is equal to 2x, and then we'll divide both sides by 2 to get that x equals y plus 5 over 2. The last step, which you can do immediately if you want to. You don't have to do it in 2 pieces. That's why I've listed them on the same step. Is that you interchange x's and y's, and then you replace y with an f inverse of x. So x equals y plus 5 over 2. You're going to rewrite that now as y equals x plus 5 over 2. And then finally rewrite the y as f inverse of x. So, a couple things. The reason why I dislike this concept is it fundamentally misses the point of what an inverse does. An inverse function takes an x and gives you a y. An inverse function takes a y and gives you back the x. So they wanted to make it look nice and like, I know what they're trying to do in pre-calc is they're trying to say, well, we like to see functions as functions of x. So let's just rewrite it that way. But that misses the point. That misses what an inverse does. It takes the y values. It really should be f inverse of y equals that, equals blah. We should write it like this. F inverse of y equals y plus 5 over 2. We really should write it that way. That it makes way more sense as we get further on in our mathematical career, because in mathematics, later on, you don't just describe functions as functions from real numbers to real numbers. You start talking about them abstractly as functions from one set to another. And then this idea of it being an x in both cases makes a lot less sense. And it makes it very, very confusing. So I have to stay consistent with the book because your homework will want you to write it as f inverse of x instead of y. But just know that I don't like it. I don't like it. I think it should be listed as f inverse of y. But It's because they don't want, like, it's stupid. It's really stupid, but there's plenty of things that are stupid in life that we still have to do, right? We have to do taxes, even though they know how much we owe, right? They know, but no, and then helping companies lobbied it so that we don't get like that you have to pay for people to figure out how your taxes are. But they could just do it for us, right? But no, that means that we can't make profits. What will happen to TurboTax? What will happen to H&R Block if the IRS just does our taxes for us? What would happen? We'd make more money. But either way, I'm getting sidetracked. Optional one is to check your work, right? That SpongeBob meme, which did I save that one in this page? Like there was one time where I forgot to include it or to delete it. No, but that SpongeBob meme of you should check your inverse, check your work, right? So verify their inferences by composing them. For us, just checking one composition will be sufficient. Just checking one is enough. It's overboard. It's perfectly checking to make sure everything works out. To check that, like if you found the inverse and you're pretty confident in your algebra, if you check one of them and you get back X, you're good. You're good. There's never going to be a time in this class where you get a left inverse or a right inverse. So it simply won't happen. So as long as you check one, you're probably good. So let's just go ahead and do that. We'll do F composed with F inverse, though you could do F inverse composed with F. So by definition, this is F of the quantity F inverse of X. F inverse we just found up above is X plus 5 over 2. So this is F of the quantity X plus 5 over 2. And so what we're going to do is we're going to replace X in the function F with an X plus 5 over 2. So this is going to be 2 times the quantity X plus 5 over 2 minus 5. And you'll see the 2's will cancel first, and then the 5's will cancel. So, I mean, we can write that extra step if you want. This will be equal to X plus 5 minus 5, which will just be equal to X. And so we're pretty confident we got it right. If one composition works out, you're going to get it right. Okay. So let's do some practice of finding inverses. Unless there's any questions on that procedure. And once again, if you like to switch, like, so the way the book will do it, the only difference is that the way they do it is they say, okay, we're going to swap it from here. We're going to make it X equals 2y minus 5, and we're going to solve for y. So you add 5, you get 2y is equal to X plus 5. Y is equal to X plus 5 over 2, and then you convert that to F inverse of X. So maybe their way makes it easier. If you like it, go ahead and do it. I just disagree with it on a fundamental level of what it misses the mark of what it means to be an inverse. Book's method. If you want to write this down, you don't have to. First, interchange X and Y. I just do it at the end. Because I like to think of it as what it's supposed to do. You're undoing what's being done to X. But, okay, let's do an example. So f of X equals the fifth root of 2x minus 9 plus 13. So step 1 would be, or step 0 would be to replace the y, the f of X with a y. So we get y equals the fifth root of 2x minus 9 plus 13. And we want to solve for X. We want to undo everything so that we get X by itself. So we don't want to take the fifth power first because that will make that, like, we don't want to do that. because then this is not going to be, this is going to have to be FOILed out 5 times, and that'll make things awful. So first what we're going to do is we're going to subtract 13. So y minus 13 is equal to the 5th root of 2x minus 9. Now what we'll do is we'll undo the 5th root by raising it to the 5th power, by doing the opposite operation. Raise both sides to the 5th power. And don't FOIL it. Don't FOIL out y minus 13. I mean, you could, but it's just going to be an awful mess when you don't really need to. And that will cancel the 5th root and the 5th power on the right-hand side. Now we've got y minus 13 to the 5th is equal to 2x minus 9, where we'll add 9 and divide by 2. So I'll show that in multiple details, but if you feel comfortable skipping algebra, be my guest. The y minus 13 to the 5th plus 9 is equal to 2x. And so that gives us y minus 13 to the 5th plus 9 divided by 2 is equal to x. And so we can do it in a quick way where we just interchange the y's and change the y to an f inverse all at once, or you can do it in 2 steps. So now it's y equals x minus 13 to the 5th plus 9 over 2. And then finally, f inverse of x is equal to x minus 13 to the 5th plus 9 over 2. And because I'm very confident in my algebra, I'm not going to check my work. More specifically, I don't have enough time left on the test to check it. So if today was a test. But I'm pretty confident in my algebra. If you're bored this weekend, verify it to yourself. I guarantee you, you will get back X no matter how you compose it. And that is how we do that one. Yes, JD.
How can we add the 9? It goes to the outside of the parentheses.
Because it's not.
Actually in the 5th power?
Yeah, because it's not being raised to the 5th power. Well, more specifically, it's just completely separate. Any other questions? Okay. These ones are nice and neat. The next one is a rite of passage for every Math 126 student. And what I mean by that is you can probably expect to see one of these on the exam. Hint, hint, wink, wink, right? I guarantee you one of these will show up. So maybe make that a note in your notes. I don't know. Maybe that'll be a helpful note to study. It's a rite of passage. It's a good problem to start your algebra skills. We're not going to be able to finish it today, which means we're not finishing 3.1 today. So I'm going to extend the due date of our quiz and our homework until next week. Just because just got a little bit we didn't finish it. That was my fault. And this should be B actually. But we'll start it off. Y equals 2x minus 3 over x plus 4. And we need to solve for x. But the problem here is there's 2 x's. And so I don't want us to panic. We see this, and then this is where we just get to play with the Legos. We get to play with the Legos. We don't have a guide to follow. We're just making stuff up. We're just trying to form our own little spaceship, right? We want to put a little rocket power here. Maybe that rocket doesn't look cool enough, so we'll take it off and try again. So point being is we'll just mess around with this and see what sticks. So someone throw out a crazy idea. What would you do? Multiply the entire thing by x plus 4. That's a good guess. It's the right guess, and it's a good choice, right? I don't like dealing with fractions. Might as well do that. So I'll multiply both sides by x plus 4. If this doesn't work out, at the end of the day, I've only added on a few extra pen strokes. Yes, it gets me closer to having carpal tunnel, but it's not terrible. And all I need to do is just erase it or cross it out and start again. This isn't killing me. This isn't life or death. So let's do that. And then we've got xy plus 4y is equal to 2x minus 3. Remember our end goal. Remember, we want to solve for x. i.e. get x equals blah. And there's just y's here. So we only want y's on the right-hand side. We only want x's on the left. Yes.
Leave it unfactored, like unfoiled.
Unfoiled, yes, you could, but you're going to see a little bit later that it actually needs to get foiled. It needs to get distributed. Because at the and that we should talk about that when we're out of time at the moment. But what I want to give you, maybe to think about it for the time being, imagine that the y was a 2, just for the sake of an argument. Imagine the y, or let's just say the y was a 1. Ignoring it for a second. How would you solve this? Subtract x and divide and add 3 to get the x's by themselves. That's going to be your key. So get the x terms by themselves. That's going to be the key. We'll pick it up next time. Once again, the homework for 1.8 is still going to be due this week. But the quiz, which has 3.1 on it, won't be due until next week. And the homework for 3.1 won't be due until next week. If you guys have any questions, feel free to email me. Otherwise, you guys have a great rest of your day. Great weekend. Your exam redo, I'm going to make it due when, did I say Monday? Screw, let's make it due Wednesday. So that you guys have chances to ask more questions if you have on it. If you have any questions on that exam, let me know. Otherwise, have a great weekend. Avoid doom scrolling. Spend time outside with friends and family. And write your congressperson. Have a great day.